Hey everybody, this is your video lesson on what are called monosaccharides, and really this fits into the larger category of talking about one of four biomolecules that we call carbohydrates. But before we can understand the structure and the function of the large molecule of the carbohydrates, we first need to understand the structure of their monomers, or their smaller molecules that make them up, and those are known as monosaccharides. If you want to just break this word down here really quickly, it's pretty easy to do. Mono, right, is a term that just means one or single, where saccharide really, if we translate it, means sugar. So the monomer of a carbohydrate is a monosaccharide, which basically is a single sugar molecule, which makes a carbohydrate just a string of individual sugar molecules. But let's take this time to learn a little bit more about how individual sugar molecules or monosaccharides are structured and some of their properties, so that you can get a little bit better understanding once we move into talking about carbohydrates. Let's start with a very, very common and very, very important monosaccharide named glucose. And what I'm going to ask you to do is draw with me the structure of glucose. So glucose is a 6-carbon monosaccharide, and we are going to draw it in what's called its chain configuration. So we're going to draw a chain of 1, 2, 3, 4, 5, 6 carbons. So that makes the carbon backbone of this glucose molecule. It's a 6-carbon monosaccharide. Then we're going to add some, I guess, functional groups, you could call them, off of these different carbons. So off this first carbon, we get a hydrogen, and we get a double bond to an oxygen. Then we get a hydroxyl group here, and a hydroxyl group here, and down here. For this last carbon, we can just go ahead and write CH2OH, which basically means it's bonded to a hydroxyl group and then 2 other hydrogens. And then every place where we did not, oh, I'm sorry, I missed a hydroxyl group on this reverse side over here. Now on the opposite sides of these carbons where we did not, where we have a hydroxyl on the opposite side, we're just going to put hydrogen. So we get a hydrogen here, there, and 2 more hydrogens covalently bonded down here. So there you go. There is the chain structure, the chain configuration of this monosaccharide known as glucose. Now, another term we can use, a little bit more general term to talk about glucose, is it is known as an Aldo Hexose. Okay, so you can call this an Aldo Hexose. And we can break this word down, Aldo, hex, and ose, to mean 3 different things: aldo, hex, and ose. Okay, aldo really means that we are going to have an end carbonyl functional group. Hex is just the meaning of the number 6, and ose means we are dealing with a sugar. So we are dealing with a 6, and what this 6 really refers to is the number of carbons. So a 6-carbon sugar molecule that has a carbonyl functional group on its end. And sure enough, if we come all the way up to this very first end carbon, we see a carbonyl functional group that you may remember from our functional group video lesson at the end of this molecule. Before we move on, I'd like for you just to number these carbon atoms. It's going to come in handy for our next drawing. So let's call this carbon atom number 1. Here's carbon atom 2, here is number 3, 4, 5, and down here carbon atom number 6. So there you go, there's your 6 carbons in this chain that make this Aldo Hexose, which means there's a carbonyl group on the end. It's 6 carbons long, and it is a sugar molecule. Now, we drew it this way for simplicity's sake, but in actuality, glucose looks much different when you expose it to aqueous solutions, or in other words, when you mix it with water, which is really how it's naturally found, especially in living systems. So the reason I had you number these carbon molecules is because things are going to start to look a little bit differently here, and you really need to follow along and try to draw this structure very carefully and slowly if you need to along with me. So don't feel afraid to pause and take your time to really draw this structure out. Okay. So what we're going to draw now is what is known as the ring form of glucose. Not a string anymore, not a chain, but an actual ring that doubles back on itself. So here's what you're going to draw. It's going to be a hexagon. I'm going to start with the top part of it, and then I'm going to put an oxygen. And then from there, I'm going to complete the rest of my hexagon. Okay. Then I'm going to start to fill out with lines. These lines just represent covalent bonds. And by the way, we're kind of getting into some organic chemistry stuff here. And when we draw these shapes, every corner of the shape represents a carbon atom. So even though this shape, a hexagon, has 6 sides, there's really only 5 corners to it because one corner is being taken up by this oxygen atom in this top right corner. So really what we see here are 5 carbon atoms, and we're going to add our 6th right up here with our CH2OH. Okay, and this line just represents a covalent bond that I just drew. At the other end of it, we're going to have a hydrogen. Okay, and we're going to draw a few more of these as well. Over here, we're going to have a hydrogen and a hydroxyl group. Down on this corner, we are going to have another hydroxyl group up here and a hydrogen down at the bottom of that covalent bond. Another covalent bond here, or I guess really 2 covalent bonds with an H there and an OH. And then our last one out here on the end with an H and another OH. Okay. So you might not be able to tell just by looking at it, but these two are actually the same thing. This chain formation is a little bit easier maybe to see what's going on, but this ring formation that we just completed is actually what glucose looks like when you mix it up with water. It forms this ring shape. If you really take the time to dissect this, you can see what we have going on here is the reason we numbered in green these carbon atoms is all the way over here we have our first. Oops, I'm sorry. Let's get this into green. We have our first carbon atom over here, represented by this corner. Then carbon atom number 2 is that corner of the hexagon. Number 3 is that corner. Number 4 is there. Number 5 is this corner, and then carbon number 6 with the CH2OH is this one that pokes off of this ring. So we really truly do have the exact same structure, only it's doubled back on itself. And the way that it did that, this is the last thing we'll draw here, is down on this 5th carbon, we have this hydroxyl functional group of the 5th carbon that is going to form this covalent bond all the way back up with the 1st carbon at the very top. So if you really take your time and dissect this and try to follow along, you can see how we go from this chain formation and we allow the 5th carbon to double back and attach to the 1st carbon with this oxygen group that kind of holds them together. Here you can see is the 5th carbon. I'm just putting a little red dot next to it. Here's the 1st carbon, little red dot, and here's the oxygen group in between them. So try to take your time and see how that might have taken place when the 5th carbon on the chain doubles back and connects to the 1st. Okay, there's one other thing that we're going to draw really quickly just for glucose, and then we actually have to talk about a completely different monosaccharide here in a second as well. But we're going to draw this almost this same ring formation. We're going to leave out some details, but just down here I'm going to kind of do a similar thing. I'm going to draw a hexagon with an oxygen in this top right corner. Finish it off. Okay, and I'm going to give the CH2OH up where it belongs. And then I'm only going to draw a couple other covalent bonds. One over here on the 4th carbon with an H on top and an OH on bottom. And one on the 1st carbon, same thing, with an H on top and an OH down on the bottom. Okay. Now I'm also going to draw a slightly different, and you'll probably be able to see why it's different, slightly different version of that same thing. So hexagon with oxygen in the top right corner. Finish off the hexagon. Put my 6th carbon, CH2OH, up here, and then off of the 4th carbon and off of the 1st carbon, we're going to have an H with an OH down here. But then this is where things get a little bit different. At the 1st carbon, we are going to have things flip-flop. Now there's going to be a hydroxyl group on top and a hydrogen down on bottom. So notice how that is different than this first one that we drew. Let me just kind of highlight it for you here. At the 1st carbon, right, we have a hydrogen on the top and a hydroxyl on the bottom, whereas over here on the 1st carbon, the hydroxyl is now on top and the hydrogen has flipped to the bottom. This is the difference between what we call alpha glucose and beta glucose. And that is something that's going to come in handy in class and a little bit later on. So you're just going to need to remember the subtle difference here between the structure of alpha glucose and beta glucose. Okay, now with that in mind, we're going to slightly shift gears here for a second, and we're going to talk about a completely different monosaccharide known as fructose. Okay. Fructose is the monosaccharide that makes fruit taste sweet. It's why apples and bananas and things like that kind of have a nice sweet taste to them because of this monosaccharide. Glucose is a very important monosaccharide for giving living things their actual energy, and that's something we'll learn about much later in class. And fructose is similar, but kind of a little bit different. So let's look at what makes fructose different than glucose. They're both monosaccharides, but they just have a different structure. So fructose is also a 6 carbon monosaccharide, but it's going to have a slightly different structure that looks like this. We're going to have our first carbon actually start with a CH2OH. Then we have 2, 3, 4, 5, and 6 carbons and a CH2OH at the bottom. So again, if we're going to just number this really quickly in green, here is 1 carbon, here's 2, here's 3, 4, 5, and 6. And then we need to have our functional groups coming off of these carbons. So off of this second carbon, we are now going to move our double bonded oxygen down here. Off of the third carbon, we are going to have, coming off to the right, just a hydrogen. Then off the fourth and the fifth carbon, we get hydroxyl groups there and there. And then remember, the opposite of hydrogen will be a hydroxyl, and therefore the opposite of these hydroxyls will be hydrogens, and we don't need anything opposite this double bond because the carbon here, the second carbon, has 4 covalent bonds. There's 4 lines coming off it, so it's okay. All right, so now what we need to recognize is that we have a slightly different thing going on here where glucose was what we call an Aldo Hexose. We just drew fructose, which is an example of what we would call a keto Hexose. Okay, so we can break this into 3 parts, keto, hex, and ose. Just like before, hex is going to mean 6 carbons, ose is going to mean a sugar. So we are dealing with a 6-carbon sugar molecule, but now this keto means that we have a middle or mid carbonyl, try to squeak it in there, a mid-carbonyl group, and that is in reference to this carbonyl group has now rotated around, so it's no longer on the end, on the first carbon. That carbonyl group has now shifted down to the second carbon. So that subtle shift in structure makes a huge difference in terms of their functionality. Glucose used for energy, fructose, completely different thing. All because we've changed the positioning of that functional group just by 1 carbon. We've just slid it down the chain to a different carbon atom. Okay, so just that slight change in functional group position makes a major, major difference in terms of functionality of these 2 monosaccharides. Just like glucose, fructose will not stay in this chain formation naturally. It will form a ring structure, and its ring structure is going to be slightly different from glucose's as well. So follow me along on this last little bit of our drawing here. For the ring structure of fructose, we are actually going to draw a pentagon with oxygen at the points. So there's our oxygen, and then we draw a 5-sided pentagon. Okay, and then off of the different points, remember the points of the pentagon represent carbon atoms. Okay, so then off the points here we have our, it's going to be kind of a tight squeeze here, but our CH2OH. Okay. Then at the bottom of that, we'll just have a hydrogen bonded there. Then let's just kind of go around here and have a hydrogen and an opposite hydroxyl. On this carbon over here, we will have a hydroxyl opposite of a hydrogen. And then off this carbon here, we will have yet another CH2OH and another, now in this case, OH down at the bottom. Okay, and just to kind of finish our numbering sequence here, our first carbon is actually this carbon, this CH2OH over here, which makes this point of the hexagon our second carbon. And then down here we have our third carbon, our fourth carbon. This point is our fifth carbon, and then up here, kind of off by itself, is our sixth carbon. Okay, so if you're wanting to try to figure out then how did we go from this chain formation of fructose into this ring formation, you'll probably see it looks something like this. We have to attach our 5th carbon, in this case, back around to our 2nd carbon, because you'll notice the 1st carbon and the 6th carbon are sticking off of the ring by themselves. So that means we need to attach our 5th carbon and the hydroxyl group there back up around to the 2nd carbon. Okay, so by attaching the 5th, and again I'll make little dots over here, by attaching the 5th back around to the 2nd, we have this oxygen that's in between them. Okay, we have that oxygen between the 5th and the 2nd, and then sitting out on the outskirts we have the 6th and the 1st carbon atoms with their H2 and OHs that are covalently bonded to them. Okay, so this is a lot to take in. This is definitely getting into some complex organic chemistry drawing, and just some of the conceptual stuff gets a little bit trickier here. But essentially what you've just seen is a couple structural differences between some very common monosaccharides. These will be important structural differences to keep in mind as we move forward in talking about the structure of carbohydrates themselves. But really, guys, the big takeaway here is that monosaccharides, or simple individual sugar molecules, are the monomers or the building blocks that are going to make much more complicated carbohydrates later. And the subtle differences in the structure of these monosaccharides makes a big difference in terms of the overall purpose of the carbohydrates that they build.